Hello, I am Kittiphop Phalakarn from the University of Tokyo. I am going to present our work with the title Constructive T-Secure Homomorphic Secret Sharing for Low-Degree Polynomials. This is a joint work with Vorapong Suppakitpaisarn, Nuttapong Attrapadung, and Kanta, Matsuura. This is the outline of the presentation. I will start with the introduction and contributions of our work. Next, I will present the related background knowledge, including non-access structure, homomorphic secret sharing, and homomorphic encryption. After that, I will explain the proposed scheme with the idea of the proofs, possible improvements, and future works. Please see the paper for more details. What is homomorphic secret sharing? Homomorphic secret sharing is a way to outsource the computation to a set of servers, while restricting some subsets of servers from learning about the secret inputs. We will consider the setting as shown in the diagram. There are input clients, and each has its secret input. The input clients secretly share the inputs to the computing servers. The goal of the scheme is to let the output client learn a function of the inputs. For security, no one should know the input except its owner. Homomorphic secret sharing can be seen as a multi-party computation protocol with small number of communications. For the applications, it enables secure computation on cloud servers, where inputs must be kept secret. It also enables secure machine learning, where the training data and models may be sensitive. In the previous work, Lai et al. Proposed a homomorphic secret sharing scheme based on homomorphic encryption. However, it is only one secure. This means any subsets of servers should not collude at all, including any pairs of servers, which is not a realistic situation. And moreover, in their suggested T-secure scheme, where at most T servers can collude, the scheme requires solving NP-hard problems and requires T-square servers. In this work, we propose T-secure homomorphic secret sharing scheme for low-degree polynomials that does not require solving NP-hard problem, and there is no number of required servers. We use the idea of secret sharing from Ito et al. To see the contributions, we will consider these 4 parameters, including K, the degree of the underlying homomorphic encryption scheme, M, number of servers, T, the maximum number of colluding servers allowed, and D, the maximum computable degree of homomorphic secret sharing scheme. The values K and D may be confusing. We start the construction with homomorphic encryption scheme of degree K, which supports computation of polynomials degree K on ciphertext. And we build the homomorphic secret sharing scheme on top of it. So the computation degree D that the homomorphic secret sharing schemes can support should be larger than or equal to K. We consider K, M, and T as requirements of the scheme. Then the number of shares and homomorphic secret sharing degree are considered as results. Firstly, our scheme increased the maximum degree of Shamir's homomorphic secret sharing scheme. Comparing to the classic Shamir's scheme, which is information theoretically secure and thus not based on homomorphic encryption, our scheme with homomorphic encryption has around K times increasing in the degree of the homomorphic secret sharing. The security models are both threshold T. Secondly, we add threshold structures to the work of Lai et al. Our work supports any value of threshold. The final degree that our scheme can compute based on degree K homomorphic encryption is shown in the bottom right. Comparing to the work of Lai et al., our final degree has a division of T as a trade-off with security. Thirdly, we decrease the number of required servers in T-secure scheme of Lai et al. In their work, only one setting of T-secure scheme is suggested. They consider the number of servers as a result, while the other parameters are requirements. Comparing to T-square servers in their work, our scheme do not have a restriction on the number of servers. Finally, it can be seen that we extend the capability of homomorphic encryption. Comparing to the setting using only homomorphic encryption, we mitigate the single point of failure by adding more servers to the scheme, and also increase the computable degree at the same time. You may notice that the number of shares of our scheme seems to be large. We will discuss about it later. In the next part, I will briefly introduce the definitions of non-access structure, homomorphic secret sharing, and homomorphic encryption. Let's start with non-access set and non-access structure. Non-access set is a subset of servers that is not allowed to reconstruct the secret. The non-access structure is a set that contains all chosen non-access sets. Non-access sets are selected depending on the situation and application. Non-access structure should satisfy monotone property. This means all subsets of a non-access set is also non-access. We can also define the maximal non-access structure as all the non-access sets that are not subset of other non-access sets. These are examples of non-access structure. We will also come back to these examples again later. The first one is 4-to threshold non-access structure, denoted by gamma 1. There are 4 servers, and any subset of size, at most 2, cannot learn the secret. The maximal non-access structure of gamma 1 is gamma 1 star. In the second example, we add the set of 2, 3, 4 to gamma 1. We call it as gamma 2. The maximal non-access structure of gamma 2 is gamma 2 star. Non-access structure can be represented as a hypergraph, where each vertex represents a server and each hyperedge represents a non-access set. We will use this hypergraph representation in the proof. Continuing from the previous examples, these hypergraphs represent the maximal non-access structures gamma 1 star and gamma 2 star. The next definition is the definition of homomorphic secret sharing. We come back to this diagram again. Homomorphic secret sharing is first introduced by Boyd et al., and we will use the definition from the work of Lai et al. In the protocol, the output client first publishes its public key and keeps the secret key only to itself. Each input client then uses the public key to generate shares of the secret input and send shares to the servers. After that, each server will combine the shares into one message according to the desired function and send the message to the output client. Note that servers should not communicate to each other. Finally, the output client uses the secret key to see the result. This is the definition of homomorphic secret sharing. The scheme consists of 4 algorithms. Key generation will be run by the output client. Then the share algorithm will be used by input clients to generate shares. Each share is sent to the corresponding servers. The evaluation algorithm will be used by the computing servers to combine the shares according to the desired function. Finally, the decoding algorithm is used by the output client to get the final result. The scheme is correct if, with high probability, the final result is equal to the case where computation is performed on the inputs. For security, let the adversary choose two different inputs and then control a non-access set. The advantage to guess the input from the shares of the non-access set should be negligible. The last definition is the definition of homomorphic encryption. The setting is quite similar to homomorphic secret sharing, but this time there is only one server. The output client first publishes its public key and keeps the secret key only to itself. Each input client encrypts its input and sends to the server. After that, the server will homomorphically evaluate the ciphertext according to the desired function and send the result ciphertext to the output client. Since all inputs are encrypted, the server does not get any information of the inputs. And finally, the output client decrypts the ciphertext to see the result. This is the definition of homomorphic encryption. The scheme consists of 4 algorithms, including key generation algorithm, which is run by the output client, encryption algorithm run by input clients, evaluation algorithm run by computing server, and decryption algorithm run by the output client. For correctness, with high probability, decryption of the final result is equal to the case where the computation is performed on plain text. For security, the advantage of the adversary to distinguish the plain text from the ciphertext must be negligible. In this work, we are interested in the homomorphic encryption scheme that supports polynomial computation with different degrees. The schemes support degree 1 polynomial, such as Elgamal or Pelia, are quite efficient. When we want the scheme to support higher degree, they become more inefficient. The example of degree 2 homomorphic secret sharing scheme is the BGN scheme, and the example of schemes with degree K are the schemes of Gen 3, DGHV, BV, and GSW. In the next section, I will explain the proposed scheme with the idea of the proofs, and then discuss some possible improvements and future works. To make it easier to understand, let's start with this simplified example. Suppose that there are 2 input clients with secret inputs A and B. The goal is to let the output client learn the value A times B. We build the scheme on degree 1 homomorphic encryption and use 3 computing servers. If we do not want any pairs of servers to learn the input, the maximal non-access structure will be as shown on the slide. In the first step, input clients generate their shares. Inputs A and B are divided into 3 parts corresponding to each non-access set. The sum of shares are equal to A and B. Next, the shares are distributed where the J server gets the share A gamma and B gamma as ciphertext if J is in gamma. Otherwise, it gets as plain text. Now, each computing server gets 6 shares. 4 of them are ciphertext and 2 of them are plain text. Note that the ciphertexts are marked with boxes. It can be seen that without secret key, combining shares from only 2 servers will not violate the security, while combining shares from all servers will reveal the secret inputs A and B. It's time for each server to perform local computation on the shares. The goal is to compute A times B. which is a polynomial degree 2 of inputs. The function a times b is divided into 3 parts, each part for each server. Server 1 will locally compute y1 as follows. Server 2 and 3 also locally compute y2 and y3. Then, y1, y2, and y3 are sent to the output client. After adding all shares together and then decrypt, the output client learns the value a times b. You can see that the calculation for each server and the output client only requires homomorphic encryption of degree 1. To describe our proposed scheme more formally, we improve homomorphic secret sharing scheme of Lie et al. By using homomorphic encryption and secret sharing scheme for any structure from the work of Ito et al. The way to use the idea of secret sharing for any structure is as follows. For the share algorithm, the I input client generates shares that sum to its input xi. Each share is corresponding to each non-access set in the maximal non-access structure. The share corresponding to non-access set gamma is given to all servers that are not in that set. And the encrypted version of the share is given to all servers in gamma. The I input client also creates shares that sum to 0 and send each share to each server. All values sent to the J server are packed in Sij. For the evaluation algorithm, we split the function f into functions f1 to fm with these conditions. The sum of f1 to fm must be equal to f. The function fj is the sum of a function gj and shares of 0 of the j server. The function gj is the sum of all monomials assigned to the j server. These monomials must be able to be computed by degree k homomorphic encryption on the j server. Each server then calculates yj and sends to the output client. For the decoding algorithm, messages from servers are summed together. The output client then decrypts the sum to see the results. For the proof of correctness, if the underlying homomorphic encryption scheme is correct, then the proposed homomorphic secret sharing scheme is also correct. The proof is quite straightforward from the way we split the function f. One challenging task in this work is to find the maximum degree of the scheme and prove that there exists at least one server that can compute each term. This is the idea of the proof. The formula for computable degree is proved using pigeonhole principle on hypergraph. As in the preliminaries, we can represent the non-access structure with hypergraph. In our setting, each hyperedge is corresponding to each ciphertext share, and each hyperedge has degree t. To compute degree d polynomial, we consider all combinations of the ciphertext. This is equivalent to choosing the hyperedges in the graph and results in dt incidences. The calculation can be performed by degree k homomorphic encryption if there exists at least one vertex in the graph that has at most k incidences. From pigeonhole principle, the total incidence is at most k plus 1 times m minus 1. And finally, we have our formula. To simplify the explanation, let's consider this example. We will use degree 1 homomorphic encryption. The 4-2 threshold structure can be represented as hypergraph A. To compute degree 3 polynomial, after choosing any 3 hyperedges, at least one vertex must have at most k incidences. If we choose 3 hyperedges as in graph B and C, the yellow vertices satisfy the constraint. This is true for any combinations of 3 hyperedges. To compute degree 4 polynomial, we choose 4 hyperedges. Choosing 4 hyperedges as in graph D, the yellow vertex satisfies the constraint. However, for the hyperedge combination in hypergraph E, no vertices satisfy the constraint. This means some polynomial degree 4 cannot be computed. For the proof of security, if the underlying homomorphic encryption scheme is semantically secure, then the proposed homomorphic secret sharing scheme is also T-secure. In the proof, we assume that there is an adversary A that can break the security of the homomorphic secret sharing scheme. Then, we can build an adversary A' according to the diagram that can break the security of the homomorphic encryption. We state the resulting properties again. Our scheme has this value of computable degree. If D and K are fixed, then M is linear in T, while in the previous work, M is quadratic in T. The number of shares is increased from M in the previous work to M choose T, but the computational complexity is the same. It can be seen that our scheme requires large number of shares, but for small t, or when t is close to M, the number of shares is not that large. For other values of t, possible improvements will be discussed next. Until now, we are only interested in threshold structures. However, non-threshold structures can also be useful. Consider 2 following structures. The first non-access structure is a subset of the second one. Both cover for 2 threshold structure and have same computable degree. Since the number of shares is equal to the size of the maximal non-access structure, the first one requires 6 shares, while the second one requires only 4 shares. So we may use the non-threshold structure instead of the threshold one. It can be seen that we combine some hyperedges together, but we do not know which hyperedges should be combined. Some combinations decrease the computable degree of the scheme. The formula for computable degree of any non-threshold structures are also not found. However, it can be computed by this integer program. The idea is to select the smallest numbers of hyperedges which is adjacent to each vertex more than k times. If we can understand this optimization model, we may know how to combine hyperedges. As future works, we will try to find the relationships between non-threshold structures and other parameters as shown in the previous slides. In the construction of this work, we only consider semi-honest security, where each party follows the protocol correctly, but may try to collude and learn the secret inputs. However, in the malicious setting, a party may deviate from the protocol arbitrarily. The input client may send different values of shares to each server. The ciphertext and plaintext may represent different values. For the server, it may send any value as the evaluation result to the output client. We will try to improve the scheme to be secure in this stronger setting. Finally, it is interesting to generalize this construction to other inner-outer schemes. It can be seen that we use homomorphic encryption as the inner scheme, and secret sharing of Ito et al. As the outer scheme. It may be possible to generalize this idea of homomorphic secret sharing construction to any combinations of inner and outer schemes. That's all of the presentation. Thank you for listening.